This dataset is a sequence of angle resolve measurements that were measured from a silicon oxide film on silicon. And it's interesting because it includes both the silicon 2P as a doublet and also the silicon 2S, which is a singlet. So we have two peaks here because we have two different oxidation states, whereas in the case of the silicon 2P, because of spin orbit splitting, we have four peaks, two for each of these oxidation states. So within these data we can see identical information from photo-emission peaks with very close energy in terms of the binding energy, and yet we see very different characteristics within the spectra. And what we'd like to do is look at the different line shapes that are required to fit these two different forms of silicon. Our ability to identify line shapes depends on the resolution of the data, and in this case the silicon 2P have peaks that are narrower than the resolution of the instrument. So what we're seeing in the case of the silicon 2P are predominantly the shapes that are a result of the instrumental factors. There are certain differences we can see. For example, the elemental peak is narrower than the oxide peak, and this is what we would expect, but we don't see any kind of valley between the silicon 2P 1/2 and the silicon 2P 3/2 peaks in the elemental form, and this we would expect to see had we used the correct pass energy for the resolution of these data. On the other hand, if we look at the silicon 2S, these peaks are sufficiently broad that the influence of the instrument, while obviously still present, is not as significant to the shapes as the photo-emission lines themselves. So we see these wings appearing here and here that are characteristic of the photo-emission process for the silicon 2S, and that should be compared with what we see with the silicon 2P, where there are wings but they're nowhere near as pronounced as the case of the silicon 2S. Because the resolution isn't good enough for the silicon 2P, we would have to impose some kind of constraints to force four peaks to fit these data. So rather than focusing on the silicon 2P, we'll go to the silicon 2S, and because we have two peaks and we have broad peaks and the shape of these peaks are dominated by the photo-emission process rather than the instrumental factors, this provides a much better target for constructing line shapes. We also have the advantage is that this measurement is a sequence of angle resolve measurements, and when we tilt the sample, what we do is we preferentially gather signal from the surface layer, and since this is a silicon oxide on silicon, as the angle is tilted away from 90 degrees, we see the amount of oxide relative to the elemental form increases until we look at 15 degrees and we see almost no elemental signal at all. There's a small feature here, but predominantly we have the shape of the silicon oxide, so this is very useful when constructing line shapes. In the first instance, we'll start the peak model based on the spectrum where we have both oxide and metal peaks, and we'll use the quantification parameters dialog window to create a background, and the background that has come in is a Shirley background, and it spans an interval. And the usual definition of a Shirley background would involve a background that meets the data at the two extremes of the interval over which the peak model will be defined. The next step would be to add two component peaks, one representing the oxide and one the elemental form. If we say fit, we end up with a fit for these particular line shapes that are not particularly good. There's a significant difference between the line shape, the background, and the data in these wings. So what I'm going to do is alter this line shape, and let's see what happens if we put in a line shape that is a GL40, and I'll apply this to both peaks, oxide and elemental form, and say fit, and once again we end up with a line shape and background that fails to model the data in these wings particularly well. So what we need to do is choose a line shape that actually works for these data and this background. Initially I will set this as an LA1,100. This is a Voigt function, and it provides signal in the wings that are characteristic of a Lorentzian, that when I fit I end up with a far better fit, at least down here, indicating that the Lorentzian for the elemental form is working reasonably well. However, for the oxide form, it is not working well with this Shirley background. In fact, what I would need to do to make this work better is to offset the Shirley background from the data. So each time I do this, I end up with a fit that would be better than the previous one, and I could do the same sort of offset over here. And the idea is that the line shapes plus the background should reproduce the data. So let's say fit once more. We can see that it is possible to produce a line shape and a background that reproduces the data reasonably well, provided we are willing to offset the background and use a Voigt function for the line shape that has a predominantly Lorentzian characteristic. And the use of a Voigt function is appropriate for both of these peaks, provided we're willing to offset the background from the data itself. One of the problems we have with this peak model is that the Shirley background is lifting beneath this oxide peak, and this is not what we would typically expect for an oxide peak. We would expect a flat background beneath it, and the rise in any background should occur as a consequence of the elemental peak. So what we would like to do is change the background type and change the peak model so that we can accommodate this idea that the background is only going to rise beneath the elemental peak. We can do this if we copy the elemental peak and paste, and then change to include a prefix that generates a Shirley background based on a specific component. So I'm going to just make a few adjustments, such as I want the full width half maximum for the background to be the same as the full width half maximum for the elemental peak, and I would also like to input some physical information. So I'm going to introduce an offset that is representative of the band gap. This is an interval in energy where the inelastic scattering or any energy loss events should be deferred until after the band gap, where electrons can then scatter and interact with electrons that are within the solid state. So if I enter B plus 1.2, this provides a position from which the Shirley background will start to rise and then become flat. So I'll press fit, and we start to see this Shirley background here is represented by a component peak. So we can see how the Shirley background, when fitted as part of the peak model, it doesn't necessarily join the data, it's offset. Now this offset depends on a number of factors, and one of them is the line shape of this oxide peak. So if I change the line shape of the oxide peak to be more Gaussian and less Lorentzian by increasing this number, if I make this say 170, I end up with a change in the line shape. You can see how the fit is altered, and when I say fit, we get a different fit, you get a different rise in the background. So the background interacts with the photo-emission line shape to determine the areas of peaks and other properties of this peak model. This is rather important when we want to work out the area between an oxide and an elemental peak. For example, if we wanted to work out the film thickness of the oxide based on the Hill equation, this ratio is the important factor in the calculation. The elemental form of the component also has an influence on this Shirley shape, and that's obvious by virtue of the fact that the line shape that I've used for the elemental form is repeated here in the Shirley shape. So if I want to change the shape of this line shape, I ought to also change the line shape within the component that represents the Shirley background. And I can do this using the hash option, and this makes use of the component index. So if I set the component index of the oxide, which I might as well enter a name now as the oxide, then the component index is the same for both of these components that represent the component itself plus the background to the component. So now when I change this amount of Gaussian, if I make this into say 60 instead of 100, and then I enter hash, when I enter hash, then the line shape is transferred to other components that have the same component index. So -1, -1, it will be transferred over here. It has a slightly different form if there's an SB prefix. That what happens when I enter hash and press return is only the LA part of this component definition will change. So when I press return, it asks me whether I want to transfer the line shape to all components with the same component index. Because the oxide has a different component index, it's okay to do this. I wouldn't want to change the line shape for the oxide, so I press return to transfer the LA line shape to the component that represents the Shirley background, and also adjust the line shape for the component itself. So now I can see that the residual indicates this has altered the fit, and I need to fit again. So we end up with a different fit and potentially a different relationship between the Shirley component and the other components within this peak model. And the importance of the Shirley component is that this is not a signal that we want to include in any calculation. So if we set the RSF to 0, and we'll indicate that this is a background, and also that we have an elemental peak. So this represents the peak model that looks like it is providing a reasonable solution to these data, but perhaps we could do a little better if, for example, we introduce a little bit of asymmetry. So if I say 1.04, that this represents a parameter that will act on the right hand side of the peak model. So the Lorentzian on the right hand side will have a different suppression to the Lorentzian that will be available to the left hand side. And if I again say hash, the same line shape applies to both, slightly different fit, and we end up with an even better fit to these data. So at this point we've got a peak model that looks like it's plausible for these data, but this is not necessarily the final peak model. There are other things that we ought to do to make sure that this genuinely makes sense. For example, we ought to make sure that when we compare the intensity of these peaks that we measure using this particular peak model to, say, a peak model that we construct for the silicon 2p, then the oxide ought to relate to the oxide in terms of percent area, and similarly for the elemental. So simply because a peak model fits is not the full story. There are other tests that we ought to do to make sure that we've got the appropriate line shape that is generating an area that allows us to quantify these data. When we've constructed a peak model that is supposed to model a thin film of oxide on elemental silicon, then if we have other data with the same characteristics, the same peak model should apply. So what we can do here for these angle resolved data is to propagate the peak model to all of these other spectra that in principle are the same material, just with different thicknesses of the oxide film. So we display in the active tile the peak model, and then select in the right hand side the spectra that are equivalent and for which the peak model should apply. And then if we right click and then propagate regions, components, and then auto fit, we can just check that the list is correct. We've got a sequence of block IDs from the same file that indicates this is the destination for the peak model, and once we're happy with this we press OK, and the peak model is then transferred to these other data. So when we step through we can see how the peak model is doing, and it looks reasonably good. It's even quite good for a 30-degree angle, but something has gone wrong, certainly in this case where it's 15 degrees. So we need to go and have a look at that, because the elemental silicon component has broadened and is taking up some form of a background shape or some structure that really isn't representative of an oxide and an elemental form of silicon. So this needs further work. If we look at these data and see why this peak model failed, then one of the things that you can see is that the background, this is a flat background upon which the Shirley background and the elemental peak are defined, that these have taken up positions because the pedestal background is too far away from the data itself. So if I make an adjustment, then you can see that the shape will change depending on the adjustment of this background. And you can see it now takes up a form that looks much closer to what you'd expect for the elemental peak. So the position of this background is important to the fitting of these data by these component peaks. The adjustments were being made to this flat background were done on the basis of changing these parameters here for the start and end offset. Now there's an alternative way of simulating the same adjustments, and that is in an equivalent way to introducing a background type. And just as the SB allowed the introduction of a Shirley background, there is another line shape that will simulate a flat background. We can add this flat background as a component by adding a new line shape. And the new line shape is SS open bracket 1, 0, 0, and this introduces a top hat function. So this is going to be a background, and because it's a background, the RSF should be set to 0. The top hat function can be seen better if I set the position of the top hat function in the same position as the oxide. So here's the flat background, but it's not spanning the entire energy interval yet. So what I need to do is make an adjustment to the full width half maximum so that the top hat function spans the entire region that the background corresponds to. And if I set that, say, to 30 for the full width half maximum, then what happens is we end up with a flat component that can be fitted at the same time as the Lorentzian-like components and this Shirley background. So before I do this fitting, what I need to do is adjust the background itself, and this can be done by offsetting so that the flat background is no longer trying to fit to the data, and what will fit the components to the data will be this top hat function, which can be optimized at the same time as the Voigt functions and this Shirley shape. So when I now say fit, we can now see that the top hat function has lifted to compensate for the fact that I'd offset the actual flat background to a much lower level than is reasonable. And the point of doing this is that I can now apply this and fit a flat background along with these components throughout this entire data set. So we've got the silicon 2S and varying proportions of oxide and elemental silicon, and I'm happy now that if I propagate, I should end up with a peak fit where I get physically meaningful elemental and oxide peaks. Let's have a look at this. This is the shape that was required in terms of a background plus component peaks that fit these data at 90 degrees. So when I go down this list, I end up with fits, and in each case the offset between this flat background has been accommodated by the top hat function. And in particular, what we need to do is see what happens for 15 degrees tilt. When we allow the top hat function to adjust so that the data are fitted by the oxide and elemental peaks plus a small contribution from a Shirley type background associated with the elemental peak, then the fit occurs and fits well in the first instance. When we have components that represent the background, the display looks slightly odd. At least it doesn't look like the normal background plus components that we're used to in XPS. So if we just look at a slightly different one of these, let's see, now we've got one here, we can make an adjustment to the display so that these components are summed if they're designated as background components. And the way a component is designated as a background in CasaXPS is to use the component index. And we can specify that components should be displayed as a background if the component index is -1. So when I tick all these boxes and press OK, what we see are colours that are assigned to the components, and they're summed in a particular way, and it depends on the component indices. As it stands, these data are being displayed as if we have one photo-emission line. All other components, because they have a value of -1, are being displayed as if they're background components. So what I need to do is specify a different component index, so I get a different colour for the elemental peak. And now we see the elemental peak, the oxide peak, and the two components that represent either a Shirley shape or the shape of a top hat function that represents the background. These both have a value of -1, therefore they're summed, so we end up with the Shirley shape background, and the components are plotted on top of that background.